So we talked about optimality criteria, and I want to describe in mathematical terms what the likelihood optimality criteria is. The likelihood of the model given the data is equal to the probability of the data given the model. Now, just as a sort of side, we have to learn how to read math. This is a language. How many of you knew that this line meant given? Model given the data. Don't get scared of these formulas. I have a hard time with math sometimes myself. But when you see a complicated formula, don't just skim over it. Try to read through it. Let's talk about some of the parts of this equation. Now, this may not have much meaning to you, so I'd like to describe it in the very simplest terms. Imagine you had a very simple data set, one taxon, one nucleotide. Somehow you collected data and you found that the single nucleotide data set is a single nucleotide A. What is the probability of that datum? Did you know that the plural of datum is data? So data are, never data is. That's another side. So what is the probability of this data point? You could figure out here by looking at this part of the equation. But the trouble is, we don't have a model. What would be a good model for the probability of collecting a single nucleotide A from a DNA data set? Well, one possibility is that the 4 nucleotides are present in equal proportion. And in that case, the probability of this data set is 0.25. In other words, we have 4 nucleotides that we could draw from a hat. We collected a data set, drew from the hat, and pulled out an A. So now we have a model that says that there's an equal probability of drawing any of the 4 nucleotides at one nucleotide. And we have a data set, A. We now have the probability of the data given the model is 0.25. The likelihood then can be calculated from the data and the model, right? Now, what if we had a more complicated tree in which we had a point in time here and a point in time here? And here we have an A, and here we have a T. What is the likelihood of this data set? Well, it's really going to depend on our model that tells us what is the probability of changing from an A to a T over this period of time represented by that branch length. So you can see that the probability is going to be fairly difficult to calculate for an entire tree with 100 taxa, because we're going to look at the probability of recovering the data under a given model. Okay? That's the simplest explanation I can give for what likelihood is trying to do. Maximize the probability of the data. Let's go back to that simple data set with one taxon. What if we had 2 nucleotides? What's the probability of the data now? Well, under our original model, the probability of drawing an A from a hat is 0.25. What then is the probability of drawing an A followed by a T? The T is also a probability of 0.25. So the probability of drawing an A and then a T would be 0.25 squared. So you can see that if we had a long set of nucleotides in a single taxon, the probability of having A, T, C, G, G, A, T, all the way to 1,000 nucleotides is very, very small, but it's still not zero, and we can calculate it. This is what likelihood is doing.